Hello everyone, welcome back to the Secrets of Calculus. Today we're finally going to clean up some of the outdated definitions that make it confusing to join this function party. Oh, is this video too long? Here's the formulas. Let me know what you did with that extra free time. So last time I ended by asking how you would define continuity. And the current definition is very bad. It's you can draw the graph without lifting the pencil. This definition is bad because even if the graph has a hole in it, like shown with g of x equals 2x times x minus 1 divided by x minus 1, the hole at x equals 1 can be filled using the limit, and therefore the limit can give out a seal of approval because no pencil can detect that hole. Well, today we're going to finally clean that up. And I gave a hint as to how you would do this by saying to start with defining continuity at a point. So, let's do exactly that. The definition of continuity at a point can be best explained by drawing a circle. The center of the circle is your chosen point, and the circle is the smallest it can possibly be while still having the graph run through it. If there is no limit whatsoever to how small this circle can be, then we can say the function is continuous. So, fair enough. Now, let's take a look at the equation set 2x times x minus 1 divided by x minus 1 and y equals 2 at x equals 1. Because the first function cannot be defined at x equals 1. The function just doesn't exist there. You'd be dividing by 0. Even, sure, you can bring in a limit, but the limit can't fill in the fact that the function itself doesn't actually exist there. This is one of those cases where being close to 1 is not equal to 1. So let's see what happens with the circle. If we put the circle at x equals 1, y equals 2, we can make this circle as small as we want to. No problem. The graph still runs through that circle. And we can say that this set of equations is continuous at x equals 1. Now, let's say we didn't have this x equals 1 means y equals 2 piece. So if we did that, there'd be nowhere to put the circle. After all, the function does not exist there. So we can say that it's not continuous at x equals 1, because where would you even put the circle? Now let's put that x equals 1 part back, but this time we'll set it to y equals negative 2. Now we have somewhere to put our circle, but what happens when the circle shrinks? We can't shrink it very far before we're no longer able to keep the graph inside. Because there is a boundary to how small the circle can be, we can say that the function combo is not continuous at x equals 1. So circles are cool and all, but how do you actually compute this kind of thing? The shrinking circle is the limit. So this limit lets us get really close to the point, which it can't do if the center of that circle is way off. Speaking of which, the center of the circle, defined as a point, is the function itself. Put together, you need both the function of the point and the limit approaching that point to equal each other. And in order for them to equal each other, they both need to exist. That's continuity at a point. But what about being continuous across an interval? Now, an interval is basically just a zillion points right next to each other. So if we were to test continuity, we would have to do this test on every single point in the interval. That is an unreasonable request. So we need to take some steps into what I'm calling big braining. I realize I didn't define big braining well last episode, so here's how big braining works. Big braining is where you know what you're doing well enough that you can take shortcuts. Mental math and intuition are both parts of big braining. Here we're going to take a shortcut to avoid testing every single point for continuity. First, look at warning signs of an unruly function. These include functions where it's possible to divide by 0, take the square root of a negative number, or take the log of a negative number, and also other illegal things. Now, if there are no trouble spots like this, we can assume that the function is continuous everywhere, from negative infinity to infinity. And other warning signs are most common in multi-piece functions, like g of x here. And the warning is the intersection of the different pieces. So once those warning signs are found, you can just do the continuity test on those warning signs and assume it's good for the rest of the function. So now that we've defined continuity in a way that means we no longer care about pencils, we need to finally put a debate to rest. Does infinity count as an answer? The general consensus is no. Even though infinity is treated like a number in this instance, saying 1 divided by 0 equals infinity is kind of bogus because infinity is technically not a number in and of itself. It should really be treated as a number that just gets really, really big. Hey, limits can do that too. We can write that as the limit as x approaches positive or negative infinity. By the way, that's coming up in the next episode. Now, just because infinity is not a number doesn't mean a limit producing it fails to exist. It just disqualifies it as a valid output from a function. So, let's revisit the function party. The organizers of the function party want square root of x to join, but only if it brings absolute values. They do not want log of x to join, even if it did bring absolute values. They want piece-defined functions like g of x to join, but they don't want 1 over x squared to join. It sounds like the barrier to entry could be redefined to be continuous on the interval negative infinity to infinity. And now that we know that the function has to equal the limit in order for the function to exist, infinity cannot be an answer, nor can that answer be found using a limit. The limit can only exist if the limits approaching from above and below equal each other. Now, what if there's no way to go above and below? Such is the case with the limit as x approaches infinity or negative infinity. Try it out yourself. How would you define the limit as x approaches infinity? Here's a hint. The limit as x approaches infinity can be seen as just a really, really, really big number. See you next time!